look up at the night sky, and the moon seems small enough to blot out with a raised thumb. It's a pale little coin hanging up there, unremarkable, easy to ignore. And that impression is, honestly, a lie your own eyes are telling you. Here's a better way to picture it. If you could somehow peel the moon's surface flat and lay it across Earth, it wouldn't just cover a country. It would cover the whole of Europe, and then keep going. Add China, add the United States, add Brazil, add South Africa, and you'd still only just be catching up to the moon's total surface area. Central Europe alone would comfortably fit underneath it, with room to spare. That's not a small object drifting past us. That's a genuine world, sitting quietly a short cosmic hop away. So why does it look so unimpressive from your backyard? Partly it's a trick of comparison. Nothing else in the night sky gives your brain a reliable sense of scale. Stars are just points of light, with no visible size at all, so your mind has nothing nearby to measure the moon against. And without a reference object, far away and enormous ends up looking exactly the same as close and small. There's a related, well-documented effect too. The moon actually looks noticeably bigger when it's sitting low near the horizon, right behind trees or buildings, than it does higher up in an empty sky, even though it's physically the same distance away in both cases and its apparent size hasn't changed at all. Your brain is simply comparing it to something else on the horizon and getting fooled by its own trick. Your eyes are perfectly capable of resolving the moon's actual apparent size, but your brain, starved of context, quietly files it away as unremarkable. Now, weight is a different story entirely. Despite being a genuine world in terms of surface area, the moon is only about 1/81st of Earth's total mass. That's a strange mismatch, and the reason comes down to what each body is actually made of. Earth has a dense core of molten iron and nickel sitting at its center, packing enormous mass into a relatively compact sphere. The moon, by contrast, is built mostly from lighter rock, with only a small iron core, so despite covering a continent-spanning surface, it simply doesn't weigh anywhere near as much as its size would suggest. But how does the moon actually stack up against Earth in relative terms, rather than absolute ones? Here's where things get genuinely impressive. Our moon is the largest moon in the solar system relative to the size of the planet it orbits. Every other major moon out there, Jupiter's Ganymede, Saturn's Titan, even Jupiter's Callisto and Io, all of which are individually larger than our moon in raw size, are still tiny compared to the gas giants they circle. Our moon, meanwhile, is more than a quarter of Earth's diameter, an oddly large partner for a rocky planet our size to have. In absolute terms, it's the fifth largest moon in the entire solar system, and it comfortably outsizes the dwarf planet Pluto, despite Pluto getting an entire is-it-a-planet identity crisis over the decades while the moon just quietly orbits along, rarely getting asked to prove itself. That disproportionate size isn't an accident either. The leading explanation among scientists for why Earth ended up with such an unusually large companion is a violent one. Roughly 4.5 billion years ago, a Mars-sized protoplanet, often nicknamed Theia, is thought to have slammed into the young Earth at an angle, rather than head-on. The collision would have blasted a colossal amount of molten and vaporized debris into orbit around the newly reshaped Earth, and that debris gradually cooled, clumped together under its own gravity, and compacted into the moon over what was likely just a few tens of millions of years, a blink of an eye, on geological timescales. If that theory holds, the moon isn't some passing rock Earth happened to capture. It's essentially made of shrapnel from Earth's own early chaotic childhood, reassembled into a smooth gray sphere and locked into a permanent orbit ever since. That unusually close, unusually large companion doesn't just sit there quietly, either. It actively shapes life on Earth in ways most people never connect back to the moon itself. The moon's gravity is strong enough and close enough to pull on Earth's oceans, stretching them very slightly toward and away from it as the planet rotates underneath. That stretching is what drives the daily rhythm of high and low tides along coastlines worldwide, a rhythm that shorebirds, tide pool ecosystems, and coastal fishing communities have built their entire routines around for as long as either has existed. Without a moon this large, sitting this close, Earth's tides would be far weaker, driven mostly by the sun instead, and the coastal ecosystems we take for granted today would likely look completely different. So if the moon really is this huge, why does it look so small in our sky? The answer has to be distance, and that's where our intuition tends to completely fall apart. Let's try building up to the real number step by step. The International Space Station orbits at about 370 kilometers above Earth's surface. Could the moon be sitting out there at ISS altitude? Not a chance. At that distance, Earth's gravity would be so overwhelming and so unevenly distributed across the moon's body that tidal forces would tear it apart entirely, scattering it into a debris ring long before it could stay in one piece. Let's push further out. Geostationary communication satellites, the ones responsible for beaming television and internet signals, sit much farther away, at around 36,000 kilometers, hovering so precisely above a fixed point on Earth that they appear to hang motionless in the sky. Surely the moon is out there, among our most distant human-made satellites? Still no. We need to go roughly 10 times farther than that to reach the moon's actual orbit. On average, the moon sits about 384,000 kilometers from Earth, a genuinely staggering distance once you've built up to it step by step rather than hearing the raw number cold. It's also worth knowing that number is an average for a reason. The moon's orbit isn't a perfect circle, it's a gentle ellipse, so its distance from Earth actually varies over the course of each month. At its closest approach, called perigee, it can be as near as around 356,000 kilometers, and at its farthest, apogee, it can stretch out to roughly 406,000 kilometers. That's why a supermoon, when a full moon happens to coincide with perigee, looks noticeably larger and brighter than a full moon near apogee, even though it's the exact same object doing the exact same thing it always does. Just how far away is 384,000 kilometers, really? A commercial 747 airliner, cruising at typical speed and flying non-stop with no fuel stops, no refueling, no rest, would need roughly 28 straight days to cover that distance, longer than most people's entire vacation time for a year. Even with the kind of dedicated spacecraft that actually made the trip during the Apollo missions, traveling far faster than any airliner ever built, the journey still took a little over 2 full days each way, meaning the astronauts spent the better part of a week just in transit before and after actually landing. And if you tried to drive there in a car, cruising non-stop at a steady highway speed with no traffic, no stops, and no need to sleep, you'd be looking at something in the neighborhood of 5 to 6 months behind the wheel just to arrive at a giant gray ball with no roads, no gas stations, and no signal once you got there. Here's one more oddity about the moon that the raw numbers don't capture. It's tidally locked to Earth, which means it rotates on its own axis at exactly the same rate it orbits us, a coincidence of physics that took billions of years of gravitational drag to lock into place. The practical result is that we only ever see one face of the moon from Earth's surface. The far side stays permanently hidden from direct view, and humanity didn't actually get its first real look at it until a spacecraft photographed it in the late 1950s, revealing a landscape that turned out to be rockier and far more heavily cratered than the familiar near side we'd been staring at for our entire history. Every full moon, every crescent, every eclipse you've ever watched has shown you the same familiar hemisphere, while an entire second face has been quietly turned away from us for the whole of human history. So, how big is the moon? Depending on how you want to define big, the answer changes completely. Big enough to blanket several continents' worth of surface area, small enough, by mass, to weigh a tiny fraction of the planet it orbits. Big enough, relative to its host planet, to be the standout oddity of the entire solar system. Far enough away that reaching it by any method humans have ever built takes real, serious time, even at the very edge of our engineering ability. Maybe the real answer isn't a single number at all. Our brains just aren't built to intuitively grasp distances and sizes on this scale. Nothing in ordinary daily life, no room, no city block, no flight you've ever taken gives you a working sense of what 384,000 kilometers, or a body 1/4 of Earth's diameter, actually feels like. That's exactly why tricks like laying continents across a lunar map or walking up through ISS altitude, then satellite altitude, then the real distance work so well. They're not decoration, they're a kind of scaffolding your brain needs, because raw numbers alone just bounce off our sense of scale without something familiar to anchor them to. It's the same reason the moon looks bigger near the horizon than it does overhead, even though nothing about the moon itself has changed. Our sense of scale was simply never built for objects this large, sitting this far away. And it takes a genuine trick, not just a bigger number, to make the true picture land. The moon hasn't changed size or distance in the time it's taken you to watch this. What's changed is that you now have something to measure it against.